so I'm going to start here on page 3. And the goal for today is to do pages 3 through 10. And in the process, we're going to learn about what are organic functional groups, what do you need to know about them, and how do we know that they exist, how do we measure for them. And so we're going to talk about infrared spectroscopy. And by the end of today, you should be able to look at these kinds of data, and you'll be able to tell me what kind of structure you might have in the compound that these spectra come from. And that will be your assignment, is just turning in what you think these compounds are. We're going to start on page 3 by talking about structural features of molecules from which I can predict their properties. Okay, so for example, I know with alkanes, they have a certain property of being chemically more stable than others. I know that they're combustible, meaning I can burn them. Gasoline is a lot of alkyl groups. In these names are the functional group name, alkyl group, that's if it's attached to something else, or as a molecule, the class of compound is called an alkane. It's in the class of alkanes. These lines mean that there's something attached to them at the end. Now, last time we talked about when we draw a line, what do we assume is right here? Do we assume it's a hydrogen or a carbon? All right, we assume it's a carbon. Very good, guys. So, so what this means here when it's not specified is it usually means carbon, but it could also, in this context, it could mean anything attached here. And it's the carbon that's attached that is the alkyl group. So it could be a nitrogen here, or it could be a, you know, maybe, I mean, not nitrogen, it could be like a many carbons. It could be a hydrogen. It could be, you know, could be some different things. But what we're focused on here is the fact that it's a carbon with maybe other carbons on it. So that's what we're referring to as alkyl group. Okay, normally what we would do is have you guys memorize these functional groups, but you know, since we're online this quarter, you'll have access to this chart, and you won't have to memorize it as much, but in the future, it's something that would be expected of you, that you would have memorized these. Here we have a double bond, meaning a sigma bond, and a pi bond. And we talked about that a little bit last time. So when you have a molecule containing a double bond, it's called an alkene molecule, or in the class of an alkene. But the group itself, if it was a larger molecule and we're just talking about the double bond portion, then it's called a vinyl group. So do you need to know both names, alkene and vinyl? I would say, yeah, probably you will see them both. Eventually we will use them both. But for now, you can focus on alkane and alkene. So these parts right here. Okay, next we have the same thing, but for a triple bond. We call it an alkyne. So you can see how we're using the language. We're just adding a different suffix, ane, ene, ein, and then they mean slightly different things, right? Okay, so I would learn these blue ones together. Alkane, alkene, alkyne. All right, next, we're looking at some nitrogens and oxygens add different kinds of properties, like some can hydrogen bond, like this guy can hydrogen bond because it's got this OH group. So the OH group is called a hydroxyl group, and this is an alcohol molecule that contains a hydroxyl group. And you guys know that with COVID, the supplies are running out on rubbing alcohol, and hand sanitizer is made mostly of rubbing alcohol or other alcohols. This carbon is attached to the OH. So I want to just make a quick note. OH by itself is hydroxide ion. This is hydroxyl group. That means it's attached to a carbon. It's not the same thing as hydroxide. Hydroxide is an inorganic ion. Alcohols contain organic, meaning carbon-based OH groups. Okay, so it doesn't dissociate like NaOH. It's not like that. Okay, ether. Ether is where you have carbons on both sides. So the ether cannot hydrogen bond to itself because there are no hydrogens here, but it could hydrogen bond to water. Okay, so it just depends on what else is in the solution. So I would learn these two together, alcohol and ether, because they both have the CO part, but one has an H and one has a C. Okay. Next, we're going to go to amine. And amine is where you have a nitrogen attached to a carbon. And this nitrogen part is called the amino group. So like amino acid, okay? And then the last one here is, on this column is the benzene ring. And this is a 6-membered hexagonal ring with alternating pi and sigma bonds. So pi, sigma, going all the way around. And you've probably seen this before. It's also called a phenyl ring. It goes by 3 names: aromatic group, benzene ring, or phenyl group. And then sometimes it's also called arene. So anyway, I don't know, you know, people have a lot of names for things that are similar. Okay, so those are all possible for that. And then notice we have more. Okay, so do you guys see the difference here? That these all have something in common, right? So I would learn them together. So I would learn, let's say in a different color here, I'm going to learn aldehyde and ketone together, because not only do they have this, but they also have that in common. And then the difference is that this has a C and this has an H.
What do you turn on?
All right, so I would learn aldehyde and ketone as it's a carbonyl with a hydrogen versus carbonyl with a
it was
carbon.
61 degrees.
All right. Next, I have a carboxylic acid and an ester. So the difference here is, well, these also have a carbonyl, but here I have an OH group and here I have an O carbon group. And sometimes we refer to these carbon groups on the end as R groups. So you might see R, and R means just any carbon group, like it could be a benzene, it could be 3 carbons, it could be 2 carbons, it could be 1 carbon. So R just means like, it's like a organic chemist version of X. Okay, and yeah, the double bonds can't be anywhere in the ring, they have to be alternating. So it has to be double bond, single bond, double bond, single bond, double bond, single bond. It has to be that kind of pattern. Okay, so from the chat box there. Okay, so the last one here, so okay, so here, and by the way, this is not carboxylic acid. Sometimes students say, well, isn't this a ketone plus an alcohol? And I would say, no, it has a totally different reactivity than either of its parts. And so I would say that's why it's listed as its own functional group. So always look for the specific thing and not just it's this one and this one stuck together. It becomes its own thing, okay? All right, same thing here. This looks like an ether plus a ketone, but no, it's not. It's its own thing called an ester. So think of this thing as one group, okay? One possible. And then right here, amide, I would think of an amide like it sounds like amine, but it has the C double bond O. So I would learn it with the amine, amide. And the difference is this C double bond O. Again, is this a ketone plus an amine? No, it's its own thing. Because they're together, they start reacting as one like family unit. So it's no longer the sum of its parts only. Okay, and then the last one is it's similar in that this is aromatic and this is an alcohol, but once they're together, they too will form their own thing. And so then it becomes phenol versus phenyl. Okay, so different names for these different reactivities and chemical, physical properties that these patterns carry with them. Okay, so this is very useful though, because when I look at a molecule and maybe I've never seen it before, you know, even going back to like, I was showing you Viagra, right? Or I was showing you benzoic acid. Like you can tell certain things just from these molecules, just by looking at them. So I know, oh, that's a phenyl ring. That's very nonpolar. Oh, here's a carboxylic acid. This can hydrogen bond. This is acidic, hence the name carboxylic acid. That's because of the H there. You know, you can look and you can see, oh, these amines here, these might hydrogen bond. So there's a lot of structural information you get from knowing about your functional groups. Okay, so on your own, when you can, just refer to this page and start learning these. And the more familiar you are, the more it's going to help you this year in organic chemistry. Okay, line bond notation. For this, basically want you to practice with looking at these kinds of structures and being able to tell how many carbons are here, how many hydrogens, how many oxygens, what is that chemical formula. Why don't we try that just on your own? How many carbons do you see in this molecule? Maybe just type in the chat or feel free to speak up and let me know. Okay, so we have 6 in the ring, 7 up here, 8, and 9. Thanks, you guys. Yeah, 9 carbons. And then let's figure out the hydrogens. So for hydrogens, you can draw them in at the beginning, but eventually you want to be at a point where you don't have to draw them in. You can just sort of see them or know that they're there. Okay, so if I draw in all my hydrogens, including the one that's already here, I've got 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then for oxygen, 1, 2, 3, 4. All right, so that's basically how you should be able to see everything without it showing explicitly. All right, and notice the hydrogen on the oxygen had to show because it's only the ones on the carbons that we assume are there. But if you're on anybody else but carbon, you need to show yourself as a hydrogen. Okay, and yeah, the carbon, yes, so functional group wise, I think I mentioned it, but I didn't write it. Functional group for this by itself is called a carbonyl group. So all of these functional groups on the right contain a carbonyl group, but I wouldn't call them all ketones and aldehydes. I just call it a carbonyl group. But to be more specific than carbonyl is very useful. Okay, all right, finally, let's go ahead and use the chart that we just came from and try to identify what functional groups are in this molecule, just so you start getting a sense of what functional groups are. So for example, and you guys can type in the chat box too if you recognize any of the functional groups. Yeah, definitely a benzene ring or aromatic group or phenyl group. I guess I would prefer to use phenyl because that's in the name of some compounds. Alcohol group, not quite, almost alcohol. It's not by itself, it's with the carbonyl. So you have to include it as a carboxylic acid, not an alcohol. Okay, so that's very important. That's called a carboxylate group or carboxyl group. If some of you guys took biology, maybe you've heard of that. And then this guy here, this is an ester, right? It's an ester because it's got the carbonyl group, has a carbon on one side and it has an oxygen carbon on the other side. If this was OH, it would be a carboxylic acid. Okay, great. So we have 3 functional groups in this molecule. So why don't we just try a couple more here. Why don't we try cinnamaldehyde down here? And again, practice with your hydrogens and practice with identifying, circle and label your functional groups. Okay, so I have 8 hydrogens and right, the ring group is a phenyl group or an aromatic group. And you can use any of these three terms. You can say benzene, aromatic group, or phenyl group, or arene group, the four choices. Yeah. And I wouldn't call it an ether because this carbon has a carbonyl. So anytime you have an ether, but it's got a carbonyl group on one of those carbons, it's called an ester. Ether and ester have sort of similar letters in their name. Okay. All right, so yeah, I would just call it ester, not ether. Carboxylic acid, not alcohol. And a phenyl group or an aromatic group, benzene, arene, any of those things work. Okay, what functional groups here in cinnamaldehyde? So this is the molecule that gives cinnamon its flavor. And you could probably already tell, like that pops out. And also in the name aldehyde, that's the aldehyde right there, cinnamaldehyde. And the alkene, very good. All right, good job, guys. So what you should do is you should practice circling to identify what is the essence, what is the piece there. You can label it. I'll just choose phenyl, but you can use any of those other terms, alkene, and then aldehyde. So on an exam, I'm most likely to have a question like this, and you guys, I would give out all the choices, and you guys would pick, okay? And it could be multiple ones in the same molecule. All right, and then one more thing that tricks people is down here with cocaine. This ring right here, it's sort of tricky. People are like, what the heck is that? So basically it goes from this nitrogen down to this carbon here, then to the back there's another carbon, another carbon, another carbon. These connect, these connect, these connect. So there's carbons in this ring all the way around. So it's 1, 2, 3, 4, 5, 6, 7 carbons in this ring. Okay, so it's what we call a bicyclic ring. So carbon-wise, that's just alkyl group. It's just carbon, hydrogen. But this nitrogen makes this into a functional group. So I would circle that and I would call that what? Should I call it? Yes, an amine, not an amide, because there's no C double bond O next to the N. So this is called an amine. Good. And methamphetamine, cocaine, all these molecules have nitrogen in them. They're from a class of molecules called alkaloids that are present in plants usually. And anyway, a lot of them have these psychoactive effects. Okay, so I think you guys can go through and do the ones on the right on your own sometime and check your answers in the answer key. Let's start with infrared spectroscopy unless anyone has questions. Okay, so for the next half hour or so, I'm going to tell you how we know, let's say, whether you have cinnamaldehyde or whether you have cocaine, okay? You walk into the lab and they're like, look, this person had this white powder. Do you know what this is? And as a chemist, you can say, yeah, let me go run that on an instrument and I can tell you if we have an aldehyde or if we have an ester or we have an amine or we have a benzene ring. There's like lots of tests we can do and instruments we can analyze these compounds with. So one of those instruments is called an infrared spectrometer. And basically what we're doing is we're just interacting these molecules with light, and the molecules either absorb the light or they don't. And there's some frequencies they absorb and some frequencies they don't. And so you can tell based on what's being absorbed, what kinds of bonds there might be. So it's really cool. You can use it for forensics. You can use it for making drugs, pharmaceutical company, making new materials. I mean, it's so useful. So to understand better about why does that happen, are we able to do that? We're going to look at this activity on page 5. And so basically, the idea is that you have molecules with bonds. And these bonds right here, the frequency of light that they absorb depends on a lot of things about that bond. Sometimes we can even think of those bonds as being like a spring, like in physics. where you have a spring that's like the bond right here, and the mass or block attached to it is like the atom. So think about the bonds, two atoms, and then the bond in between, that it's sort of vibrating like a spring, like a mattress spring. Okay, so I want you to think about this. Which has a higher frequency or, rate of bouncing, a strong spring or a weak spring, assuming the same mass is attached? So which will bounce faster if you have a strong, stiff spring or if you have a weak, skinny spring? Okay, strong. Maybe a couple people are saying weak. Yeah. So, okay, well, write down your prediction. And then for part B, let's think about if we have the same spring, so pick stiff or weak, whatever, but you have a different mass each time. So you have a light mass versus a heavy mass. What will happen to that bouncing? Okay. So maybe it doesn't matter which mass you have, but yeah, let's picture it. You have a spring here. You put something light on it, and you drop it. It's gonna bounce. Now take that off and put a heavy thing on there. Is that gonna affect the rate of that bouncing, that frequency? Okay, so go ahead and put in which you think would have a higher frequency or which would bounce faster, a lighter weight or a heavier weight. Okay, now let's try this. We're going to use this physics simulation, and we're going to see what the answer might be to that. So I'm going to go to a site, maybe some of you guys know about it, called Physics Education. A group has this simulations page, and there's one on masses and springs. So if you're interested, it's called fet.colorado.edu. And I'm choosing the masses and springs, and I thought I had this set up beforehand, but there it is. Okay, so now what we're gonna do is we're gonna try playing around with different things to answer those questions. I'm gonna look at the first question, which is what happens as we change the strength of the spring. So I'm gonna take this 100-gram weight, and just with the spring that I already have, I'm just gonna drop it and sort of note how fast it's bouncing up and down. Okay, you guys sort of have a visual of that now. Okay, so that's how fast that was. And now I'm going to increase the stiffness of that spring. How strong is that spring? And now you guys maybe can visualize it better and think to yourself, oh, was I right before? Or what's gonna happen to how it bounces now? And you guys can tell right away, it's bouncing a lot faster. So the stiffer that spring is, or the stronger the spring is, the higher the frequency of that. There. Okay, now we're going to go back to the regular spring, and we're going to try different masses. So I'm going to go back to that 150 that we had before, and we're going to test out the effect of changing the mass. Okay, so with the same spring, I'm going to go ahead and look at this again. This was the first one we did. That's with 150-gram weight. Okay, and now you guys had to predict what would happen if I changed the mass. And now let's say I have something heavier. Can you guys see how that's going to be different? And so I'm going to let go, and you're going to see that it's a lot slower. So the frequency does change with both of these things. The strength of the spring matters, and so does the mass that's attached to it. So for the first one, the higher rate of bouncing was from the stronger spring. And then from the changing the mass, we saw that the lighter weight is going to allow for faster, higher frequency. Okay. So along those lines, if a chemical bond is like that, then I would look at the mass of the atoms attached as having an effect of the frequency of light that is being absorbed. And then I would also look at the bond itself. Is it a single bond, a double bond, a triple bond? These have different strengths. All right. Now so let's skip this for just a second. So which of these would have a higher frequency of light that is absorbed then based on those two factors. So I have single bonds of carbon to hydrogen versus carbon to oxygen. So focus on what's different about those two. Yeah, it's the H versus the O, and the H is lighter than O. So this should have a higher frequency. Okay, good. And how about these guys? CO single bond versus CO double bond. Who would absorb a higher frequency of light and bounce faster? And so this one, you want to think about the bond as the spring. So yeah, that's right. Thank you guys. Yeah. So C double bond O. Okay, so the double bond has a stronger bond than the single bond. So it's got that, it's like a stiffer spring. Great, now up here, it sort of shows you what the molecules do when they're absorbing these frequencies. So when I have just the right frequency of light, which is usually in the infrared spectrum, so it's a lower energy than visible light, when it absorbs some of these energies, it takes it and it does these, it stretches around, it bounces and it stretches and it does all those things that the spring was doing, okay? So I'll just show you real quick. Another little tool online for that is called Models 360. And this is sort of cute because it sort of shows you a molecule here. Here's arsenic acid. And then basically with this molecule, you can look at its vibrations. By selecting those frequencies, you can see if I had energy with this light. So it's basically just rotating around, and it's not rotating, but it's stretching. It's doing these kinds of weird movements here. Okay, so that's what that actual frequency of light is doing. And there's different frequencies that it absorbs. And so you can see the little graph here showing you different frequencies, and they each have different movements and different stretches for that molecule. Okay, so that's what's actually happening with that light. So let's look at the different values of those stretching frequencies. And you can see again on the left here, we're talking about infrared spectroscopy. That is here on the spectrum of light, from radio waves being like the lowest energy, X-rays being the highest in this chart. And infrared is pretty low energy. So we have a laser with infrared light. Okay, and now over here, these are some of the frequencies of that infrared light that we use. And you can see for each sort of region that we have different kinds of bonds that absorb that light. So if you are an alcohol molecule, you are going to probably absorb in this region here. So those are some ideas for me as a chemist. If I see a peak at 3200, I'm like, oh, that could be an alcohol, or that could be an alkene, or that could be an alkyne, or, you know, like right here, 3300 is almost in that range also. So basically, I'm looking at this bond right here. Okay, so these are some of those values that you guys would be looking at to identify what kind of functional groups are present. And it's really cool in lab to do this because it's like the first time some students realize that these are real molecules, and you can actually, you can't see the molecules, but you can see direct evidence of what you have in your hands. It's a really, really cool thing. Okay, so I would say of these in the chart that I've highlighted, the ones that are really, really common are the OH. So I would definitely try to learn these at some point by next quarter. You will be memorizing them. Okay, not this quarter, but next quarter, you will be memorizing some of these values. Okay, but for now, you guys can just use the chart. Okay, no need to memorize at this point. Just try to use it and see how useful it can be. These are the two really important common ones that you see. And then also you see the alkane, because alkane groups are everywhere, alkyl groups, carbon, hydrogen, it's just like every molecule has that. And then you have alkene, which is also very useful to know, those guys, okay? So those are probably the most useful ones that I would highlight. All right, let's do a little bit more here and then you guys will get some practice. Theory-wise, I had attached a video to the pre-lab assignment for today. Some of you guys saw that. The way that the instrument works is I'll show you this little diagram first, and then I'll show you what the actual instrument looks like. You have usually like a laser, a lamp or a laser that shoots light of different frequencies, usually in the infrared spectrum, shoots those frequencies as waves of light. You can see they have different frequencies, right? Some have higher frequency, lower frequency. They go through at the sample. Some of them go through the sample and some of them get absorbed and do not go through, okay? Because they're absorbed and used by the molecule to stretch and do all those things I was showing you. All right, the frequencies that make it to the detector basically give you this line right here. So this line is for all the frequencies that are detected, and then as there are frequencies missing from the detector, you start getting these peaks. And so we usually graph percent transmittance. Transmittance means it made it through. Absorbance means it didn't make it through to the detector. So we have 100% transmittance, then 0% transmittance and 100% absorbance, and then transmittance, oh, we're getting absorbance, and so forth, okay? So these points, again, these are where nothing is absorbed. So those are these lines right here. And then the energies that get absorbed, or the light that gets absorbed, are what's creating these peaks. And they do look upside down. These are upside down peaks because we are graphing transmittance or absorbance inverted, okay? I think you're used to absorbance going up. And so if I flip this, that would be the case. But for some reason, someone chose to do it by transmittance, okay? All right, and the last thing is the units for this are frequency in wave numbers. So that's right here. This is the x-axis is wave numbers, and y-axis is transmittance, or percentage transmittance out of 100%. Okay, so you can write that here if you want. Okay, let's go down and look at a real spectrum. Of course, you can go back and answer those questions if you want a little bit more detail with that and practice with the theory. But let's go ahead and look at this molecule. And let's say that I took this sample and I ran it on the infrared spectrometer. Okay, by the way, what does that look like? This is what the infrared spectrometer looks like at Bellevue College. We use an FTIR, meaning Fourier transform. It's got a little disc here, the laser's inside, and it's got a diamond crystal right in the center where that thing is clamped down. So basically, we have this version where instead of passing the light through the sample, we pass it up into a diamond crystal. Then it interacts with the light, it interacts with your sample and bounces through the crystal and then goes to the detector. So it's a really, really easy to use because you just put the sample right on top of the diamond. Whether it's a liquid, you just pipette drops on there, or if it's a solid, you can clamp it down onto the diamond. Okay, so that's the instrument there. So let's say we put a couple of drops on the diamond, the light from the laser is coming through, it's bouncing through your sample, and these are the peaks that are absorbed. This is the light, the frequency of that infrared that's absorbed. Couple of things I want to show you real quick. Number one is we've got this OH group right here. So how do I know that? Is this molecule has an OH group. I would look at the chart, since you probably don't have it memorized, feel free to use the chart. You've got something in the range of, 3,000 something. And now there's a range because it does vary. I guess I would say if you could just maybe memorize one value and just say it's around that value. I remember just one value because it's easier to remember one value than a range of values. So when I think alcohol, I think 3,300. When I think alkyne, I also think 3,300. When I go to alkene, I sort of think 3,100. So these are some go-to numbers for you as you start to become familiar. 2900 versus 3100 tells me if I have an alkene versus an alkane hydrogen. So this is a sp2 carbon, this is a sp3 carbon. So that changes its frequency. And then the last one here, I would just remember this as 1700. Okay, and these are all wave numbers, inverse centimeters. Okay, so centimeters to the -1. Sorry, that's what that says. Okay, so what I would do is, okay, alcohol is 3,300. That's why I see the peak right here, 3,300. I see some small peaks, and it's not always clear when do I need to know the small peak or when is it just an artifact or something that's not important. I think through experience, you sort of get that. So I would say, though, anything that sort of past this 50%, like it's sort of definitely a peak, right? Like this is definitely a peak. This is maybe not a peak up here. So these guys are probably peaks that you should take seriously. So if you look here, this one falls at like 28 to 2,900. And then this one right here is more like 3,100. So, and again, this is, does that look like a mistake? Maybe. Okay, so sometimes in real life, it's not so easy to know. You might use another technique just to verify. But you know what? This peak at 3,100, if I look at my chart, 3,100 says it's an alkene. What else is in an alkene is a C double bond C. And we know C double bond C happens here around 1600, 1650. So if I look here and I see that, that's a confirmation that I probably do have an alkene, right? Because I'm seeing both of those things. So, okay, so it's a lot of information. I feel like this is a OH group here. That's from this guy. We have this guy and this guy. That's due to these. And then I have this 2,800-ish. Is 2,900 is from the alkane. All right, and then the last thing is notice this fingerprint region is basically anything past or below 1,500. I would sort of disregard usually because it's very specific to this particular molecule. It can be used for exact matches if I ever needed to know for sure. Is it really this compound or does it just happen to be coincidental? Then I can use this fingerprint region. But there is one peak in the fingerprint that is sometimes useful, and you can see it right here at 1,100 is the CO bond right here. That can be sometimes be useful to try to find that, but it's usually very messy down there. So I usually don't want to deal with it. Okay, but that 1,100 is on the bottom right here. 1,100 is sometimes useful for ethers or alcohols if you don't have anything else to go by. Okay, so I think that's enough information for you to maybe try out some of these on your own. So normally in class, I would be showing you each how to run the infrared spectrometer, show you how it works, like in person, and you would run the sample and actually do it yourself. And so it's sort of cool, but you know what, you'll have a chance to use it next quarter, hopefully, or the quarter after that. So I think it'll be okay. Yeah, if it's 3,300, then it's, sorry, Rasmina has a question. If it's 3,300, then is it either alcohol or alkyne? Why not an alkyne? Yeah, very good question, Rasmina. Sometimes in real life, you know, it's very complicated and there's millions of molecules and I really don't know. Like this peak here could be because it's 3,300. How would you really know the difference when both of these are 3,300? That's Rasmina's question. So that's a good question. In the real world, if I had nothing else to go by, I wouldn't know if it was this one or that one. But for the triple bond, I could at least look for this peak as well, right? I could look for C triple bond C and look if there's a 2,200 lying around. Okay, so then that would mean it might be an alkyne. The other thing though is notice some of these say broad, strong. Okay, strong means very intense, very deep peak, very big. Broad means sort of like U-shaped. Okay, so alcohol is very characteristic to be broad, and you could see this U shape here. That's due to the hydrogen bonding effects. So that's why I know it's an alcohol from looking at it. But otherwise, these peaks that are sort of deep, those are called strong. Okay, and some peaks are stronger than others, and you will learn that by experience.